Okay, hello everyone. Today we are going to learn about chapter 3, discrete random variables and their probability distributions. This is second course of chapter 3, and we are going to learn about some of well-known discrete random probability distributions. The first one I'd like to introduce is Bernoulli probability distribution, and I think this is the the simplest distribution in discrete random variable. So, what would be the simplest one in? Uh, could you imagine it? Maybe tossing a coin? Yes, it is. Tossing a coin, something like that. So a trial results in one of two outcomes, success or failure. So this is the simple one. And random variable which takes the value 1 with probability p and the value 0 with probability q, which is 1 minus p. So when we are tossing a coin, it have head with probability p. For the balanced coin, it's 0.5, and the value 0 with probability again 0.5 when it is balanced coin. We say it as y follows Bernoulli distribution p. So we will write it in this way, and also the example is a coin toss. The second distribution is binomial probability distribution. Probably some of you maybe heard about it, and let's define it. Experiment consists of a fixed number of n identical trials, actually n number of identical Bernoulli trials. Each trial results in one of two outcomes, success or failure. So we have some series of Bernoulli trials, sequences of Bernoulli trials, and each have sometimes success, sometimes failure, sometimes success. Yeah, okay. And probability of success on a single trial is equal to some value p and remains the same. Thus, probability of a failure is 1 minus p. So, success with probability p and failure with probability 1 minus p. And trials are independent. So, each of these trials are independent. And random variable of interest is y. Y is the number of success observed during n trials, and it is sum of each Bernoulli trials. So in Bernoulli trial, it is 1 for success, 1, 0, 0, 1, 1, and the random variable y is sum of success, sum of the number of success, and here this time it is 3, and the binomial probability distribution is the distribution for this random variable. And we say y follows binom np. So um, for this kind of distribution, we say this way. And here, for this example, it is y follows binom how many 5, and with probability p. I don't know if it is balanced coin toss, would be 0.5. Okay, so this is binomial probability distribution. Okay, let's go through example 3.5 to understand binomial probability distribution. An early warning detection system for aircraft consists of 4 identical radar units operating independently of one another. So we have 4 identical radar units to detect aircraft for early warning. Okay, and suppose that each has a probability of 0.95 of detecting an intruding aircraft. When an intruding aircraft enters the scene, the random variable of interest is y. Okay, the number of radar units that do not detect the plane. Okay, here it's do not detect is the interest, and is this a binomial experiment? Okay, let's check one by one. Experiment consists of a fixed number 4 of identical trial. Okay, actually, experiment consists of 4 identical Bernoulli trials, and let's see. We have 4 identical radar units operating independently of one another, and so for the radar, we are interested in the event of do not detecting. So do not detect is 1 and detect is 0. And okay, so experiment consists of fixed number of identical trials. That's okay. And second, each trial results in one of two outcomes, success or failure. Yeah, success, um, do not detecting intruding aircraft, failure, detecting intruding aircraft. Okay, so it is true. And the second, probability of success of a single trial is equal to some value. The probability of do not detect is 1 minus 0.95, which is 0.05, and remains the same for other radars, and the probability of a failure is 0.95, which is detecting the aircraft. Uh, okay, and also trials are independent, and random variable of interest is y, the number of successes observed during the 4 trials, which is sum of 4 Bernoulli trials, and uh, so as a result, this random variable y follows binomial experiment. So we can say that y follows binomial distribution with n equals 4 and p equals 0.05. Okay. Let's go another example. Example 3.6. Suppose that 40% of a large population of registered voters favor candidate Jones. A random variable of n equals 10 voters uh, n equals 10 voters will be selected, and y, the number of favoring Jones, is to be observed. Does this experiment meet the requirement of a binomial experiment? Okay, this is our second example, and let's check one by one. Experiment consists of fixed number 10 of identical trials. We are randomly sampling 10 voters, so it would be okay. And each trial results in one of two outcomes, success or failure. So what in a large population, uh, we are observing the number of favoring Jones. How many people favoring Jones? So favoring Jones would be success, and do not favoring Jones is failure for a given sample. Okay, and probability of a success on a single trial is equal to some value. Here, 40% of large population of registered voters favor candidate Jones, so the probability is 0.4, and the probability of failure is 0.6. And trials are independent, and random variable. Oh, actually, here, the the uh, actually in here trials are independent, and actually this is true because it is from a large population. um, if it is very small population like 3 or uh, 5, if we have 5 and 40% of population favoring candidate Jones. So 2 of them favoring candidate Jones, and then trials are not independent for small populations, because if you sample one thing and this guy is favoring Jones, then the remaining ones, there's only one people, so 25% of population is favoring Jones for now. So it would not independent for small population, but for a large population, um, even if you select one, the remaining probability is still 40% of voters favoring Jones. So for a large population, we can assume that trials are independent. However, without this large population assumption, this may not true. And the probability of success on is not equal to some value for remaining events if it is small population. But for not for this one, since we are assume a large population, um, this one holds, and random variable of interest is y, the number of successes observed during 10 trials. Here the random variable of interest is y, which is the sum of Bernoulli trials, sum of the number of uh, people who favoring Jones. Okay, so we can say that y follows binomial distribution, n equals 10, and the probability of favoring Jones is 0.4. Okay. Okay, for definition 3.7, a random variable y is said to have a binomial distribution based on n trials with success probability p. Okay, so success probability is this one. So let's check why this is true. Uh, for a binomial, for the event, a simple event could be represented as this of n letters. Each is Bernoulli trials, success, failure, success, failure. So there's n number of letters, and each one is Bernoulli trials. Success for one, and failure for 0, and 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 we are interested in the Bernoulli trial, which is the sum of the Bernoulli trials, which is the total number of success. Okay, and probability for a simple event, it is, we have y number of s and q number of n minus y number of failure. So, and probability for success is p. So for a given simple event, the associated probability is this thing. We have y number of success with probability p, and we have n minus y number of failure with probability q. So this is an associated probability for a given event, and for y equals y, there are n choose y number of events. So here we have n number of positions, and we are choosing y positions for success. It is n choose y number of events is possible for y equals small y. So the related probability is this one. The number of events times the probability of one simple event. Okay, and this, thus summing up y equals 0 to n, the p of y, it is 1 by binomial expansion, and with this one, py, the py is equal to this one because of this, and by binomial expansion, summing up this thing can be represented as this, and q plus p equals 1, so 1 to nth equals 1. Okay, so yeah, this is binomial probability distribution. And let's check how it looks. So here's here's binomial 10.1. If y follows binomial 10.1, the histogram is shown here, and this is for binomial 10.5. And if there's a little chance of success, then the distribution would be skewed to the left. But if it is the fair situation for each Bernoulli trials, then it's centered at 5, and yeah, the shape looks like this. And for when we have a large number of events, when we have 20 numbers, here y follows binorm 20 and 0.5, and it looks like this shape. And actually it looks like kind of bell shapes. And actually we were going to prove that when n goes to infinite, when n goes to large, we can approximate this as normal distribution. We were going to learn in the future, but some of you maybe already learned it from another class. But yeah, you will going to learn from this class as well by central limit theorem. Okay, let's move on to example 3.7. Suppose that a lot of 5,000 electronic fuses contains 5% of defectives. If a sample of 5 fuses is tested, find the probability of observing at least one defective. So the problem is find at least one defective, and what would be the probability of the number of defectives. So you sample 5 fuses, and what the the number of defectives would follow binomial distribution. So if you define y as the number of defectives among 5 fuses, then you can associate the probability distribution of y as binomial distribution with n equals 5, and p equals the p probability for defectives as 0.05. And the probability you are interested in is probability of at least one defective. So at least one defective means that it is 1 minus no defectives. So you are in if you know probability of no defectives, then you can find probability of having at least one defectives using this way. So probability of at least one defective, it's actually probability of y equals 1 plus probability of y equals 2 plus plus yeah, y equals 5. And since summing up all the probability is 1, so probability of having at least one defective is 1 minus probability of y equals 0. And so this is 1 minus p0. And from the definition of binomial distribution, it is the p0 is 5 choose 0 times p0 q fifth, and this is result in this number. Okay. Let's go to the next example, example 3.8. Experience has shown that 30% of all persons afflicted by a certain illness recover. A drug company has developed a new medication. 10 people with the illness were selected at random and received the medication. 9 recovered shortly thereafter. Suppose that the medication was absolutely worthless. Suppose that medication is worthless. What is the probability that at least 9 of 10 receiving the medication will recover? What is the probability that at least 9 of 10 receiving the medication will recover? Okay, so what would be the related probability distribution? What can we define as random variable y? The random variable y could be the number of patients who recovered. So number of patients recovered. Okay. If we set our random variable y as this, then what distribution this thing follows? So y maybe would be follow binomial distribution, because each trial could be Bernoulli trial with probability p, which is 30%, because suppose that the medication was absolutely worthless. So if medication is worthless, the probability of recovery follows the experience, which is 30%. So y follows binomial distribution with n equals 10 and p equals 0.3. And the next question is, what is the probability that at least 9 of 10 receiving the medication will recover? Which is probability of at least 9 will recover, and this is probability of the binomial y equals 9 plus probability of y equals 10. And from the definition of binomial distribution, you can calculate p of y equals 9, and also you can calculate p y equals 10, and by summing up those two probabilities, you can get the answer for this example. Okay, here is theorem 3.7, and this is about the mean and variance of binomial random variable. Okay, so how can we calculate the mean and variance of binomial random variable? By definition of 3.4 and 3.7, the expectation y is defined as this way, and the probability of y, the py for binomial distribution, can be represented as this. And from here, when y equals 0, the part inside is 0, so you can the summation could be y can start from 1 to n, and also here n choose y. The definition of n choose y is this one, so we replace it with this, and then here y and y factorial, the first number cancels, and so this becomes y minus 1 factorial, and from here actually, from here, the strategy we'd like to take is we want to make this as a form of binomial distribution, summation of the binomial distribution, and summing up that binomial distribution could be 1. So to make that possible, we want to make this sum as y equals 0 to some number. So to do that is y minus 1 equals 0 to some number. So So we want to define y minus 1 as different number. So here, actually, this can be rewritten as 1 of n factorial can go out and 1 of p can go out. And so here, to make this as y minus 1 and y minus 1 factorial. And if we want to let y minus 1 as z, if we want to let y minus 1 as z, then the z, when y equals 1, z equals 0. So if we, this summation becomes this, the z becomes 0, and the summation z is from 0 and y equals 1 to n. And actually, when n is n minus 1 factorial, so when so from here y equals 1 to n, and when n is inside of here, this is n minus 1 factorial, and n minus 1 is actually m. We want to specify that as m, so this sum is from z equals 0 to m, and since n minus 1 is m, so it is m factorial, and here n minus 1 and y minus 1, this is n minus y as well, so this it becomes m minus z, and this becomes z factorial, and p to this, and q to m minus this. And here we can see that this is the sum of binomial distribution with n minus mn p. The related distribution is binorm m and p. So the sum of this thing equals 1, and so this, the result is n times p. This is the expected value of y. I mean, okay, let's move to the variance part. For variance part, we'd like to use theorem 3.7, which is this thing. Variance of y is expected value of y squared minus the expected value of y squared. Okay, so however, if we directly use calculate this number, we will encounter some problem. So expected value of y squared is this thing. However, it's kind of tricky to solve this. So the trick that we use here is to apply similar trick. We use this one. Ey squared is actually ey squared minus y plus y, and this will becomes to ey times y minus 1 plus ey. Okay, so we will calculate this one. We already know this, which is np, and we'd like to calculate this one. So to calculate this one becomes this, and here this y times y minus 1 cancels from here, and y minus 2 factorial is to be left. So here y minus 2 factorial is left, and we get 2p's to here, and we get n times m minus 1 to here. And from here, we can use the similar trick. Let z equals y minus 2 and m equals n minus 2, and then becomes, and then this part becomes 1. So this one results in this thing. And after plug in this number to the above formula, you can calculate the result. If you plug in this number to here, and this number to here, and this number to here, you calculate all these things, that result in np times 1 minus p. Let's look at example 3.10. Suppose that we survey 20 individuals working for a large company and ask each whether they favor implementation of a new policy regarding retirement funding. If in our sample 6 favored the new policy, find an estimate for P, the true but unknown proportion of employees that favor the new policy. Okay, so here the question is we want to estimate the P, uh, the true unknown proportion of employers that favor the new policy. Okay, and what would be the random variable y? How we define y? Actually, this is the number of individuals who favor a new policy. So the y could be the number of individuals who favor new policy. Okay, then the y would follow the binomial distribution with n equals 20 and p, which is unknown, and we'd like to estimate this p. And what we observed is 6 favored the new policy among 20 individuals. So the probability of y equals 6, if we assume the binomial distribution on y, the probability of y equals 6 is this one. And and so the next question is with what p probability of y equals 6 maximized? Um, Actually, here we'd like to find an estimate for p, and we observed this one. We observed y equals 6, and with what p, observing the probability of y equals 6 could be maximized. So we want to find our estimate p that maximize our observation of the data. So we want to, so this part is constant and this part is function of p. So this part is function of p, and we want to find the p that maximizes this value. Okay, so that's the problem, and actually we will use the log trick. So this is our original function fp, and maximizing this fp is actually saying as maximize log of fp. This log function is continuous increasing function. So the maximizing fp is actually equivalent to the finding value p that maximizes fp is equivalent to finding value that p maximizing ln fp. So we are going to find the p that maximizing ln fp, and where does it have maximum? As you already learned from the calculus class or calculus in statistics class, if you want to find the maximum value, you can have derivative of p equals 0, and if you have f second derivative of p equals less than 0, then you at this p it have local maximum. With this condition hold, you are going to have local maximum at point p star, and we want to find this p star position. Okay, so let's get started. We want to get the value of p that maximizes this function, and firstly we take log of that function, because taking the value p that maximizes original function is actually same as one that maximizing log of f function. So we take log from here, and then that becomes 6 of ln the ln these times can be converted as plus, and ln 6 go to the front, so 6 times ln plus 14 times ln 1 minus p. And after getting derivative, this ln the derivative ln is 1 over p, and the derivative of ln 1 minus p is actually or 1 over p, and times 1 over p 1 minus p derivative, which is minus 1. So we have minus sign here, 6 over p minus 14 over 1 minus p, and set this 0, and solve it for p. Then you will going to get p equals 6 over 20. Check this by yourself, and also check the second derivative. Check the second derivative of this, which is get the derivative of this with respect to p one more time, and then put this value 6 over 20, and then you will going to check that that value is less than 0. So the p equals 6 over 20. This would be our estimate for this p. Homework for chapter 3.4 are these. Chapter 3.5 is about a geometric probability distribution, and the geometric random variable y is the number of Bernoulli trials needed to get first success. Okay, what would be the situation of this? Let let's think about events of Bernoulli trials. So E1 would be success. Success on first trial. So here the geometric random variable is the number of Bernoulli trials needed to get first success. So here it is y equals 1. What about E2? This case y equals 2. Uh, so first failure on first and success on second. What about E3? First success on the third trial, and which is y equals 3, and for this event it is y equals 4, and for y equals k, we have k minus 1 number of failure in the front, and then you get success in the last. So the related probability for this would be the probability of getting y minus 1 times of failure and the success for the final event. So the related probability, Bernoulli probability for failure would be q, and q y minus 1 times p, which is success in the last time point. So this is the probability for a given simple event. And okay, and we say that y follows geometric distribution p in this case. Here is definition 3.8. A random variable y is said to have a geometric probability distribution if and only if p of y is this one. Actually, you have already seen the situation from the slide above, in the previous slide, and the example figure 3.5 describes the geometric probability distribution of p equals 0.5. So it looks something like this. The success from the first time, which is 0.5, and first time you fail, but success next time. Here, fail, success, fail, success, and so on. Every time the probability it decreases about half because the probability is 0.5, you are multiplying the probability of failure each time. So decrease about half, decrease about half, decrease about half, decrease about half. Okay. Okay, let's look at example 3.11. Suppose that the probability of engine malfunction during any 1 hour period is 0.02. Find the probability that a given engine will survive 2 hours. Okay, so what would be the uh, related probability distribution? So here, what would be our y? Our y would be the number of events, number of hours, a number of periods, number of period before the number of periods to get the first success, to get first success. Here we have success, here we have success, and for the event, the probability that a given engine will survive 2 hours, which means this situation. For this situation, it failed in one hour and some minute. It failed here, so we are getting the probability of these events. So here y follows geometric distribution of 0.02, and you are getting interested in finding probability of y is greater than equal to 3. And actually this probability is 1 minus probability of y equals 0 and minus probability of y equals 1. And from the definition of geometric distribution, probability of y equals 0, which is the probability of success in the first time, which is 0.02, and probability of getting y equals 1, which is first time you failed and second time you success. And after getting the number, the calculation of this, you get the solution for this problem. Okay, now let's look at theorem 3.8, which is about the mean and variance of geometric distribution. So from here, we are interested in expected value of y, e of y, and by definition, this can be written as sum of y equals 1 to infinity, because geometric distribution is defined from 1 to infinity, and y times p of y. Okay, and this becomes sum of y equals 1 to infinity, y times py. Py is p q, because p at last we have success probability p, and for the y minus 1 positions in the front, we have failure with probability q. So this is our distribution density for geometric distribution, and from here we will going to use this trick. Actually here we have y times q of y, y times q of y minus 1. And actually this is dq d q of y. So if you get the derivative of q of y, you get y times q of y minus 1. So you will put it here. So here you can get p outside since it's constant with respect to y. Y is 1 to infinity, and y times q to y minus 1, this becomes the q q of y's, and actually this summation and derivative can be interchanged with some condition, but it's above the graduate level, so for now we will just change the direction of these two. P times dq d summation of q to y, y equals 1 to infinity, and here q is less than 1. If q is less than 1, then I think you learned the formula from the statistical calculus or calculus class, or I'm not sure whether you learned this from high school calculus. But anyway, if you learned it, the formula for this series is 1 minus q, and the first value when y equals 1, it is q. And to get the derivative of this, this one can be written as q minus 1 minus 1, 1 minus q minus 1, because q minus 1 plus 1, q minus 1 plus 1, okay, plus 1. Okay, and you get the derivative of this thing with respect to q, dq this. The constant derivative of constant is 0, and derivative of this is 1 minus q square times 1, actually times minus 1 times again 1 minus q derivative is minus 1, so minus 1, which is 1 over 1 minus q square. So the result is p times 1 minus q square, this one. And actually this 1 minus q square, 1 minus q is p, so this becomes 1 over p. And so this is the solution for the first thing. Okay. And for the variance part of the formula, again we will I will just give you some hint for the exercise problem 3.85, which is the deriving the variance part. Here we will again use this, and also note that the derivative of 2 times of qy is this one. So you can, from this hint, you can calculate this. By definition, it is sum of y times y minus 1 and p q to the y minus 1, and probably you multiply q here and minus 2, and set these together as this, and with some time-consuming calculation, you will get this formula. Okay, you can do this by yourself. This is exercise problem for you, not the homework, but you can do it by yourself. Okay, next slide is for example 3.12. If the probability of engine malfunction during any 1 hour period is 0.02, and y denotes the number of 1 hour interval. So here, y denotes the number of 1 hour interval until the first malfunctioning. Find the mean and standard deviation of y. So here, y, what would be the related distribution for y? Y denotes the number of 1-hour intervals until the first malfunctioning, and the probability for malfunctioning is this 1-hour period. Then the Y, it follows geometric distribution with P parameter P equals 0.02, and find the mean and standard deviation. So find E of Y and find V variance of Y. And from the previous slide, we learned that E of Y is 1 over P, and V of Y is Q over P square. This Q is 1 minus P, and so you can calculate this. E of Y is is 50, and V of Y is, you can calculate it by yourself or using calculator, and you will get the solution. And example 3.13, suppose that we interview successive individuals working for the large company discussed in example 3.10, and stop interviewing when we find the first person who likes the policy. If the fifth person interviewed is the first one who favors the new policy, find an estimate for P, the true but unknown proportion of employees who favor the new policy. Okay, here, we stop interviewing when we find the first person who likes the policy. So the random variable y, the number of events to get the first positive, would follow geometric distribution with probability p, and we'd like to find this p, and what we observed is y equals 5. We observed this thing. The fifth person interviewed is the first one who favors the new policy. So this is what we observed, and we'd like to estimate this p that maximizes this probability. So to solve this, this function is fp, and actually maximizing fp is same as maximizing ln fp. I mean, finding the p that maximizes this local maximum of this, and this is same as finding ln fp. So you get ln fp, which is ln 1 minus p fourth times p, which is 4 times ln 1 minus p plus ln p, and you get the derivative of this, and here you'd like to find something like this. You want to find p star that p star is less than 0, then it should be, this is our fp, and with p star this condition will hold. So get the derivative of this, it will be 4 1 minus p minus and plus 1 over p, and set this as 0 and solve it for p, and you will get something by solving this. And also get one more derivative. Here you get derivative of p square d ln. If you get derivative of this thing with p one more time, and then let's just say p star is this one, put this one inside of here, then you can check that the resulting value is less than 0. So then your estimate of this thing is the answer for this example question. Try it by yourself and check it from the textbook. Okay, thank you. Here are homeworks for chapter 3.5 and okay, thank you.